Hey Chem Kids, it's Campbell here, or for Andre, it's Cam in a hood. Well, we're not really in the hood, right? So I couldn't really say that. We're at Lafayette. In our first video on gas laws, we're going to talk about gas properties in the kinetic molecular theory. We're going to talk about the three main postulates of the kinetic molecular theory and see how that relates to gas properties. Now, what's really bizarre about gases is that no matter what they all are very similar and they behave very similarly. In fact, it doesn't matter if they're a single particle, like neon, or helium or argon, or if they are two atoms together, like hydrogen or oxygen gas, or even polyatomic, like carbon dioxide, or that stinky stuff from cows' methane. They all behave very much the same. And this is something that really interested a couple guys back in the 1800s, Ludwig Boltzmann in Austria and James Clerk Maxwell, who is Scottish. They both were observing the behavior of gases, and they came up with very similar theories. And these theories are called the kinetic molecular theory. And what the kinetic molecular theory does, it explains the behavior and characteristics of gases. Now, we're going to have to talk about ideal gases. So, ideal gases are like perfect gases. You know, that person you always want to be but never are? Well, perfect gases fit the kinetic molecular theory, and most gases behave like a perfect gas. There are some conditions like maybe high pressure or low temperature where they don't, but for the most part, all gases behave this way. So it's a good model. So we're going to go through the three basic postulates. The first one is that gases are composed of small particles that take up almost no space. Like they have no volume, and they're separated by lots of empty space around them. Now, because of this, they are so far apart from each other that they don't really affect each other. They don't exert any attractive or repulsive forces, so they're kind of like hanging out by themselves. The second postulate says that they're always moving. You know, it's like the person that doesn't sit still, Eric. They're in constant random motion, and the only time they really interact with each other is if they collide with them. Now, when there are these collisions, either with each other or with the walls of their container, they're what's called a perfectly elastic collision. Now, you'll learn a lot more about elastic and inelastic collisions in physics, but an elastic collision would be like this case. If I dropped a ball and it would bounce back to the same height every single time, which we know never happens, right? All collisions are really inelastic. So only an ideal gas has totally elastic collisions in that they don't lose energy. Now, when there are these collisions, though, right, there's pressure. If you think about it, right, if you collide with something, boom, right, you feel pressure, right? That's force. And that's, in fact, what is exerting pressure when I have a sample of gas. It's these collisions of molecules with the walls of their container. The third postulate is that the energy or the speed, really, of the gas particle is actually related to the temperature. It's directly proportional to the absolute temperature. Absolute temperature is the Kelvin temperature, which is going to be very important in the gas laws. We're going to be working always in Kelvin. Now, what it means is that if it's directly proportional, if one goes up, the other goes up. So if it gets hotter, the molecules are moving faster. And if it's colder, the molecules are moving slower. So let's talk now about gas properties as they're related to the kinetic molecular theory. The first thing is, and you know, maybe this seems like a duh, gases have mass. Well, of course they do, right? They're atoms, and atoms have mass. We find it on the periodic table. But you don't really think about gases having mass, right? Because it's such low density, right? If we could actually weigh the air in this room, it would be difficult, but we could do it because gases have mass. But when we walk through them, we don't really think about it, right? You don't really feel it. It's not like walking through a liquid, which puts up a lot of resistance, or a solid, which you can't even walk through unless maybe you're a ghost, because gases have very low density, right? They occupy volume. Even if the molecules themselves only occupy a little bit of volume, the gas itself occupies the volume of whatever container it's in. But because density is mass over volume, right, if we take a look at my little box here full of gas, right, we see there's not a lot of mass in this big amount of volume. Whereas if I look here at a liquid of maybe the same molecule, here it occupies a lot less volume when it's a liquid, and as a solid, it's really smushed together, right? Which also leads us to the next idea of gas properties, which is the fact that gases are compressible, right? There's lots of room between these particles, so I can squeeze them together, whereas I can't squeeze a solid at all, right? Try to squeeze a rock. It's not going anywhere. Squeeze a liquid? Sure, a little bit. We can move those molecules closer together, but with the gases, we really can't. All that empty space between the molecules allows us to compress them. The last property of gas I want to talk about is the fact that gases diffuse, right? They're in constant motion. According to the kinetic calculator theory, they're moving all over the place, which means that they will spread out and fill up their entire container. Now, we can take a look at this from an example standpoint. Here I have some bromine vapor, gas, in a container separated from some air. And if I open this little valve here, right, the bromine is going to start flowing into the air, and the air is going to start spreading out to the bromine because they're constantly moving. It's totally random. It's not like they're trying to mix. It's just, they just happen to do that because they're moving all over the place. That'll happen actually until the concentrations of both are equal. Now, the fact that gases diffuse, right, is the whole purpose behind the whole air freshener market, right? You plug in an air freshener, and eventually you smell it throughout the room, right? If it only smelled over by the outlet, that wouldn't be very effective. Of course, that's also the principle behind when you cut it in class. You know, they say, whoever smelt it, dealt it. It's usually because, you know, that's who smells it first, right? And then you don't want anyone else to know that it was you. So you're like, oh, who cut it, man? Well, gases diffuse, so eventually everybody smells it. But then it goes away, right? Because it keeps moving. Now, let's get back to this idea that gases exert pressure. Pressure is actually defined as the amount of force per unit area. And this pressure comes from the fact that there are collisions between the gas molecules and the walls of their container. Now, remember we said we could model, the kinetic molecular theory models gases as little particles. So I have some bouncy balls here, and I put them in a little container. There they are. All right, if they're moving, right, you can hear the collisions, right? You can hear the collisions. They're exerting force, and that creates pressure. So every time there's a collision, these gases are exerting pressure. Now, anything that increases the number of collisions or the speed of the collision will increase the pressure. So, for example, what could I do to this box so that I could increase the speed or the frequency of collisions? Well, one thing I could do is I could make the box smaller, right? If I make the box smaller, then it's not going to take as long for them to hit the walls, exerting pressure. I could increase the temperature, right? If I increase the temperature, remember, temperature is related to the energy, which is the speed of the molecules. So if I increase the temperature, it's like going, or if it's really cold, it's like, in fact, that's why they tell you to take your air pressure in your tires after you've driven it around a while, because then the tires have warmed up. Tire pressure, as you can see in our little picture here, increases as temperature increases. What else could we do? Well, what if we put more balls in? Right? If we add more molecules, we increase the pressure. It's like the little lungs here, right? When you breathe in, you take in more molecules of air. And then you breathe out, you get rid of some molecules, so the pressure goes down. So increasing molecules, increasing temperature, decreasing the volume, all of these things would increase the pressure in a gas because it changes the amount of collisions.